Okay, everybody. So we're going to go ahead and get started. So this video is up very late compared to previous videos. That's because I've been about for the last 6 hours or so trying to get my main computer working here. Um, so the deal is that I got a new VR headset, which is very cool. And in order to use it, I had to install about 2 years worth of Windows updates to my desktop PC. Um, it did not go quite as expected, and in fact is still going. It just says working on updates 98%. And yeah, could I reboot it right now? I could, but there's like a very good possibility that if you reboot a computer before it finishes the updates, the next thing you're going to see is that Windows decided to roll back the update and I can't touch it. And, it's very sad. But anyway, the point is that I haven't had a working computer all day, and so I had to set up another computer for this video, which may or may not be working, but we'll see. So yeah, let's hope for the best. Anyway, let's go ahead and get started. So what we're going to be looking at today is section 5.4, which is recursive algorithms. And we'll just go ahead and get right into it. So we've seen recursion before in this class, right? We've seen we've seen recursively defined sequences, right? And what those were they were a sequence whose definition referred to other elements of the same sequence. So in the definition, to compute elements of a sequence or terms of a sequence. So to compute elements of a sequence, you needed other elements of the sequence. Actually, I don't like the way I'm writing that. Let me restart that there. So in the definition, you compute new terms of the sequence from terms that you've already computed in the sequence. New terms in the sequence from other terms in the sequence. Right? And so something like this, right? Where you go A1 equals 1. And then you can say like A n equals 3. A n minus 1 plus 2. Something like that. That would be a recursively defined sequence. Now we've also seen like recursively defined sets. We saw that in the previous section, 5.3. So that would be something like this, where you say, like 1 is an S, 3 is an S. That's your kind of your basis step. And then you would say, if, A is an S and B is an S, then A plus B is an S. And so what we're doing there is you're defining with this bit right here, you're defining new terms of the sequence, from the set, from terms that you already know are in the set. So let me say that. So elements in the set are computed from other elements in the set. All right. And in this section, we are going to have recursively defined algorithms, or just recursive algorithms. So recursive algorithms. So the idea here is that if the formula, what happened there? The idea here, we lost the video. It's back. Let me double check everything's plugged in here. Okay. So the idea is that for a recursively defined sequence, right, the formula for a term in the sequence comes from other terms in the sequence, right? So basically, the formula for an refers to itself, another an, right? An an and another an has a different index, but it's still one of the ans. So the formula refers to itself. And same thing for a recursively defined set. We want to know what's in the set S. And what's in the set S is, well, if you know two things that are in S, then you can compute another one. So if you want to compute something in S, you have to look at other elements of S. So to compute a new one, you look at old ones. Same thing here. To compute a new one, you look at an old one. And the same idea is going to apply to a recursive algorithm. So this is going to be an algorithm that refers to itself. An algorithm that basically contains a reference to itself. And I'll say that a little nicer in a second. So the way you normally would like to think about a recursive algorithm is in computer science, it's going to be, typically this is going to be a function that calls itself. It's a function that calls itself. And that's probably the way you want to think of it. And, you know, it's not exactly the same as the other recursive stuff that we've seen, but, you know, that's what it is. So we'll look at some examples here. Let's see here. I'll give you, I guess for my first example, I'll give you one that's not actually in the book because it is in the homework that you guys did instead. So, so here's an example. So you guys have computed Fibonacci numbers before, right? So let's see. So like a non-recursive you know, Fibonacci calculator, Fibonacci number calculator might work like this. So I'm going to write kind of MATLAB code here, but so let's just remember what Fibonacci numbers are, right? So the idea is F1 is 1, F2 is 1, and then after that, Fn is going to be Fn minus 1 plus Fn minus 2, right? And so if you wanted to write MATLAB code to do this, there would be a lot of different ways to do this. So you would do something like, you know, function. Let's just say like fib. Actually, that's not. Say like function f equals fib n. Okay, so in the way that we've calculated Fibonacci numbers before, what we did was we actually calculated everything, like all of them up to n. And that's what we're going to do here as well. So like, how would you do this? You would say like, you could say f1 is 1, f2 is also 1. Now I know that you can call this function with a 1 in here, so I'm going to have to be careful about how I give the answer. Actually, let me do this. Like capital F there. So F1 is 1, F2 is 1, and then we can do like for I equals 3 up to n, which will not happen if n is less than 3. Then what you could do is you could say Fi is Fi minus 1 plus Fi minus 2. Int. Now, at the end of this loop, what you've done is you've calculated all of the Fibonacci numbers up to n and potentially extra, right? Like if you call, oops, like if you call fib1, for example, it's still going to do both of these lines right here, right? It's going to do f1 is 1 and f2 is 1. But then it won't do this loop because, n is going to be less than 3. So it wouldn't do that. But it'll do both of these, right? And potentially this. And then so what you can do just to make sure that this capital F has the right number is you could just say like capital F equals Fn. There you go. Semicolon, semicolon. And then we could end the function right there. And that should run. I'm not going to test it or anything, but it's the kind of function we wrote before. The only thing that's different compared to the homework that you guys have completed is I think that probably we didn't just pull off one number, right? All this line does right here is pulls off the Fibonacci number that I'm supposed to be calculating. So if you call like fib1, it just is going to, say answer 1. And if you call like fib, whatever it is, 10, you're going to get like answer 55 or something. I don't know if that's right. I think it might be right. But you're not going to see all of the Fibonacci numbers 1 through 9 because this line right here is just going to calculate, whatever the 10th one is, store it in capital F, and capital F is the return variable, right? And so that's a non-recursive Fibonacci number calculator, very similar to what you've seen before. But we can do it with a function that refers to itself. And so if you take a look at this definition right here, right, you can see that calculating a Fibonacci number just requires you to know 2 other Fibonacci numbers. So you can write a recursive Fibonacci number calculator like this. Recursive Fibonacci number calculator. So how would it look? Well, we can say function, let's say, I don't know, capital F again, why not? Equals, let's say, rfib, so recursive fib, rfib in. Okay, and so here's what you would do. So the first case is up here. If we have a 1 or a 2, we should return 1. So let's make sure we do that. So you could say if n equals 1, or 2 vertical lines, n equals 2. You could do it that way. Or if you know that you're going to have only positive numbers, I'm not checking the input for correctness, but let's just say that that n is going to be a positive integer. You could just say if n is less than 3, right? Because the only possibilities there are 1 and 2. So if n is less than 3, then what should we return, right? We're in the case where we should be returning a 1. So you'd say capital F equals 1. Else, so if n is not less than 3, so n is 3 or more, then what is f? Well, the way you would calculate the Fibonacci number is going to be the Fibonacci number for n minus 1 plus the Fibonacci number for n minus 2. Right? So this right here is just copying this formula. Fn minus 1, Fn minus 2. That's what the Fibonacci number is. Int. And there you go. And so that's a recursive formula because you have the function declaration here, but it calls itself here and it calls itself here. So the function actually calls itself. Yeah, so there you go. So again, does that run? Probably, but I could always type something wrong here. Let's do another one, right? So let's try another one. So let's think about factorials. Another example. Let's do a non-recursive factorial. Now, what's a factorial? So just remember, right? So a factorial is like this. If I wanted 5 factorial, that means 1 times 2 times 3 times 4 times 5, right? That's a factorial. So in general, you would say that, n factorial is equal to n times n minus 1 factorial. That's going to be kind of the recursive definition because you've got a factorial referring to another factorial. But also, you could just use this formula, right? N factorial is 1 times 2 times 3 up to n. So what I've got here is this is kind of a recursive way to do it. This is recursive because it's referring to itself, right? Factorial on the right-hand side as well as the left-hand side. And this right here is non-recursive. So if you wanted to write a function for this, what the function would look like is going to be something like this. So you'd say function, I don't know, let's just do f again. Let's call it factorial. So let's say fact n. Again, I'm not going to check this. Whoa. Lost the video again. And we're back again. I don't know what's going on, but as long as it keeps kind of working, that's good with me. So, oh, it's out back. Okay. This is not great. Okay, anyway, function, factorial. So if we're doing a non-recursive factorial, you would probably do it in a loop. So, and I'm not going to check this input for correctness. I'm just going to assume that you gave me a positive integer, right? Otherwise, this is going to fail. But so here's what you could do. You could just say, so I'm using f for my variable, so I'll say f equals 1, start there, and then we'll do a for loop. So for I equals 1 up to n, all we're going to do is we're going to say f is going to equal the previous value for f times I. And int. And I think that'll do it, right? Because this is going to loop through 1, 2, 3, 4, 5, 6, up to whatever. And every time what we're going to do with that I value is we're going to multiply the I value times f. So f is starting out as a 1. So it's going to do 1 times 1, which is 1. And that's right for 1 factorial. Next time through, it's going to multiply by 2. Next time through, I is going to be 3, and you'll multiply by 3, and so on. So this would compute a factorial. And we use a for loop for it, right? Actually, now that I've written this, I believe that I'm going to just cut this out and move it here because this is our non-recursive version of that. All right, so what would the recursive version look like? Well, for the recursive version, we're going to do basically the same thing, but we're going to use, well, this kind of idea. The way you calculate n factorial is it's n times the previous factorial. So you would say like function f equals, let's say r fact for recursive factorial, r fact n. And so what you would do is you would say, well, if n is 1, what's n factorial? It's 1. But if n is bigger than 1, which I'm just putting in an else because I'm assuming that we're given a positive integer here, then the way you would calculate the factorial is you would say the factorial is going to be whatever the in value is, and then you would multiply that by the factorial, which is r fact of the previous factorial, right? So what you got here is, right, you've got the n minus 1 factorial. And so this is your n minus 1 factorial. And this is your n factorial. End. So again, you see that this function here, r fact, is going to call itself, as long as it will call itself when you give it an n value bigger than 1. And so all of these recursive formulas are kind of set up this way, where what they're going to do is they have like a base case. Like if n is 1, we're not going to call ourselves. If n is 1, we're just going to return 1. But if n is not 1, then the function calls itself. Same thing over here, or up here, right? There's kind of a base case. If n is less than 3, so it's 1 or 2, if n is 1 or 2, then this is the value we're supposed to return. But if n is bigger, then the function calls itself. Okay? And those are recursive formulas. Anything like this is a recursive algorithm. Or I wrote functions directly, but there you go. Those are some recursive algorithms. Let's see here. Let's do this one because it's in the book. The ones that I did now are not in the book. Actually, in Factorial is. So, oh, actually, I'm going to change this here. I just looked at the books and I noticed that they do this. If n is 0, the factorial is 1. And that's just because by definition, 0 factorial is 1 and 1 factorial is also 1. It doesn't really, it doesn't make a difference in this case, but if you change that to a 0 like this, then the function now gives correct output for the case where n is 0, where previously it did not, but now it does. Okay. So what we're going to do now is we're going to look at a greatest common divisor, right? So let's see here. So here's an algorithm. We're going to look at it. So let's do greatest common divisor, GCD. All right. So I think you guys know what the GCD is, right? Maybe. So let's see here. Hold on a second. Okay. So greatest common divisor, right? That's like, well, what it is. The biggest number that goes into both numbers, right? So like if you do GCD of, let's say, I'm trying to think of a good one. Let's say 25 and 15, right? You know, the largest number that goes into both of these is 5, right? That goes into, divides in evenly into 25 and 15 is 5. So that's the GCD. So GCD 25 and 15 is 5. All right. And, you know how to do that by hand. You know, maybe a couple different ways. Like you could find the prime factorization. So like 25 is 5 and 5. whereas 15 is 3 and 5, and then you just say, oh, well, this has a 5 and this has a 5, right? So then 5 is the GCD. But what's an algorithm? How would you write computer code that does that? And so I'm going to show you the book's algorithm, and then we'll try it out on an example. So this is algorithm 3 in the book. Algorithm 3. Algorithm 1 is in factorial, and algorithm 2 is like calculating a to the n, which is a very kind of trivial example. So algorithm 3, computing GCD. So here's what it says. Procedure, right? This is the book's pseudocode. So they use the word procedure, GCD, A and B, of course. And those are going to be non-negative integers, non-negative integers with A less than B. Okay. So you have to put the small number in first. So actually, like the way I wrote this up here, to make this the way they want you to write it in for their function, I would have to write it in this way, 15 and 25, because the A is supposed to be the small number. That's not a rule for GCDs in general. That's not a math rule. That's just their algorithm rule. So I don't have to rewrite what I just did, but still, I just will. All right. So this is the function. GCD AB for non-negative integers with A less than B. So they say if A is 0, then return B. Okay. Else, return the GCD of B mod A, comma A. And that's it. That's the entire procedure there. So you can see that there's definitely some advantages. That did not do what I thought it was going to do. Draw a new box. The third time is the charm. Hey, it is. Okay. So that's their procedure for computing the GCD. Let's just try it on an example. We'll have to remember modular arithmetic, so hopefully we can. So let's say they do, no, okay, I want numbers that have something in common. So, well, I guess let's just try it for, GCD 15 and 25. So let's just kind of run through this for, run through the algorithm. Actually, maybe not. Let's do like 8 and 12 for GCD 8 and 12. Okay, so what is that GCD, by the way? Hopefully you realize, so the biggest number that goes into both. So the biggest number that goes into both of those is going to be 4, right? 4 goes into both of those. So let's try the code. So, all right. So when we first start out, we've got the 8 and the 12. I don't know what the best way to write this is, so this is going to be awkwardly written. But we have 8 and 12, right? So then what we're going to do is we're going to say is, actually, maybe I don't have to keep track of that many. I'm going to try it this way. We start out, we have 8, A equals 8, B equals 12, right? And the code is very simple here. So if A is 0, return B. Well, A is not 0, so we're not returning B. So instead, what we're going to do is we are going to return the GCD of B mod A, comma A. So what we got to do is we got to figure out what that's going to be. So the GCD of B mod A, comma A is going to be the GCD of, well, what's B? B is 12. 12 mod A, nope, what's A? A is 8. 12 mod 8, comma 8. Okay. So remember what the mod is. So when you do 12 mod 8, we're saying if you divide 12 by 8, what's the remainder? So 8 goes into 12 one time, and the remainder is 4, right? When you divide 12 by 8, the remainder will be 4. So you're going to end up with a 4 there. And what's the b? The b is going to be 8. So we have this. Okay, so now that's a new function call. So we're going to check, is a equals 0? No. So we're going to return the GCD of b mod a, comma a. So what's that going to be? Well, it's going to be the GCD of b, which is 8, mod a, which is 4, comma a, which is 4. All right, so we're going to have a equals, all right, 8 mod 4. So what's the remainder when you divide 8 divided by 4? So 4 goes into 8 2 times with remainder 0. So we're going to get a 0. And then b is going to be the 4. All right. So now we're in a new function call for GCD. So we say if a is 0, then return b. Well, a is 0, so we return b. So finally we return b, which is 4. So we return 4. And that's your answer. Okay, so it looks like this function is going to work, right? So you call GCD here, but GCD will call itself with these values. That GCD will call itself with these values. And this one finally returns 4. So you just get 4. Okay. All right. I just wanted to do that example. I thought it was interesting. All right. So we're going to talk about recursive searches now. So let's see here. Yeah, let's go ahead and do that. So now let's talk about MergeSort. So this is what your programming 3 is about. Programming homework 3. Okay, so what is MergeSort? So what MergeSort is it's a searching algorithm where you merge lists. Okay, so let's see, a recursive sorting algorithm. So a recursive sorting algorithm that works as follows. All right. So before we kind of get into actually what the details are for MergeSort, so here's an idea. This is how this works. Sorting a long list is hard, right? So sorting a long list is hard. Sorting a list with 2 things in it is easy. Right? sorting two things is going to be very easy, right? Because either like if you have like 3 and 5, right, then you do nothing because that's an order. But if you had 5, 3, you would, switch them around, switch the order, and you would have 3, 5, right? So if your list only has two things in it, it would be a very easy thing to do. Okay. Um, yeah. Actually, I kind of even want to back it up further and say sorting a list with two things in it is pretty easy, but you know what's even easier than that? Sorting a list with one item. That's going to be even easier, right? So what we're going to do with MergeSort here is we're going to have two pieces to it. So the two pieces to MergeSort are as follows. Are as follows. Why do I keep saying as follows? Are these. All right. So first of all, what we're going to do is we're going to have one algorithm that just takes a list and splits it into two pieces. Okay. Um, say it's not really an algorithm, but what we're going to be able to do is split. We can split a list into smaller lists in half. Um, into two halves. That's not going to be that hard to do. Um, and then what we're going to do is we are going to, if we have two lists that are already sorted, we should be able to put them back together in order. So if you have two sorted lists, we need an algorithm that will put them back together and keep them in order. Merge them, you would even say. And into a sorted list. All right. And if you can do both of those two things, then you're going to be able to sort a list. So I'm going to show you how it looks before we actually get like code or an algorithm. So here's a list that we're going to sort. So example, we're going to sort, let's see, 8, 2, 4, 6, 9. Actually, there's just kind of long. Well, no, I'll keep going. 9, 7, 10, 1. So this is in the book, but they actually have a list with 10 things, and I'm doing a list with 8 things, just to make it easier for me to show you. Yeah, okay. So here's how it would look. So the idea is this. So what we're going to do is we're going to start by splitting the list into two halves over and over. And if we keep splitting it in half and splitting the halves into halves, we're going to end up with lists that only have one thing in it. So let's write that. So we're not doing any sorting at this point. We're just splitting. So we're just splitting in half. Half. How does that look? So we're splitting in half. So what that means is that, over here, we're going to get the 8, 2, 4, 6. And over here, we're going to get the 9, 7, 10, 1. Okay. Now, each of those two halves need to be split in half. So we do it again. So you split this in half. So you split it into an 8 and a 2, and the 4 and the 6. Same thing here. You split this into the 9 and the 7, and the 10 and the 1. Again, notice there's no sorting yet. We're only splitting the list up. Split this into an 8 and a 2, a 4 and a 6. Over here, we got a 9 and a 7 and a 10 and a 1. All right. So at this point right here, everything has been split up. So right here, everything is split up. So now what we're going to do is we're going to start putting everything back together. So we're going to, let's see, merge back together. So once the entire list has been taken apart, we're going to put them back together. But here's the key. So the idea is you're thinking of like this 8 and this 2 as individual lists, 8 and 2. And we're going to say, well, 8 with only one thing in it is a sorted list. 2 with only one thing in it is a sorted list. So if we have an algorithm that does this, 2 sorted lists, merge them together into a sorted list, that algorithm would put the 8 and the 2 back together, but when it puts them together, it's going to put them together in the right order, and it's going to have actually a 2 and an 8. Because it's going to know, it's going to just basically not check, it's when it merges them, it's going to keep them in order. So 8 is sorted, 2 is sorted as a list, put them together, you get a sorted list, 2, 8. All right, same thing here. So the 4 and the 6, put them together. You put them together and it's going to keep them sorted. So it'll be 4, 6. Same thing here, 9 and 7. It puts them together. You'll get 7, 9. And then here, you're going to get the 10 and the 1. And you're going to get 1, 10. Okay? Well, now you're going to take those 2 element lists and you're going to put them together. So we're going to take these and we're going to merge them together into a list. Now, again, this is sorted. This is sorted. We're going to put them together and it's going to keep them in order. Not like 2, 8, 4, 6. I mean, it's going to put them together into a sorted list. So that means it's going to know, it's going to basically do this. It's going to look at the 2 and the 4 and say, well, which one of those is smaller? What the 2 is. So it's going to put the 2 first. And then now it's going to say, well, what about the 8 and 4? Which one's smaller out of, right? We already did the 2. So we're only looking at 8, 4, and 6. So it's going to say 8 and 4. Which one's smaller? 4. So now it's got the 8 and the 6 left. It's going to say, look at the 8. Look at the 6. Which one's smaller? 6. Then look at the 8 and, oh, well, actually we're done. So it's 8, right? So that's how it's going to work. So it's going to put them together into a list like this, and it's going to stay sorted, 2, 4, 6, 8. Right? Same thing here. It's going to put these 2 together. And again, it's going to, basically it works by comparing the first element to the first element. So it's going to get the 1 first. And then now it's going to look at the new first element, which is going to pull off the 7, then it's going to pull off the 9, and then 10 is going to be left over. So now we have 2 lists that are sorted, this one and this one. Well, it's going to put those together. It's going to keep them in order. So it's going to compare the 2 and the 1. It's going to find the 1. Then with the 2 gone, maybe I'll even kind of this way. So we already did the 1. So now it's going to look at the 2 and the 7. Well, if you compare 7 and 2, the 2 is smaller. So it's going to put the 2 here. Did the 2. Then it's going to look at the 4 and the 7. The 4 is the smaller number. So the 4 is going to go there. It's going to look at the 6 and the 9, sorry, the 6 and the 7. The 6 is a smaller number. So I'm going to put the 6 right there. It's going to look at the 8 and the 7. The 7 is the smaller number. So I'm going to put the 7 there. It's going to compare the 8 to the 9. 8's the smallest number. So it's going to put the 8 there. Uh-oh. Low on storage space. Hope the video doesn't run out of space. All right. And then what's going to happen too is if one of the lists runs out of things in it, so like there's still a 9 and a 10 here, it's going to know, oh, we don't actually have to compare anything now. We can just take this 9 and 10 and we can just throw it on the end there. And what do you get? You get something like this, which is a sorted list. The result. Sorted result. All right. Now, what can happen when you're performing this MergeSort algorithm that we actually just performed here is that the only reason that it worked out so nicely where it was split into, and everything was even down here was because I started out with 8 things, which is a power of 2, but that's not always the case, right? You could have an odd number of elements, or you could have not an odd number, but a non-power of 2, and it looks slightly different if you have that kind of thing happen. Like, I'll just show you one more real quick here with, let's say, I'll show you one more with a smaller list. So example. So let's just sort, I'm just making this up. So let's say 7, 3, 5, 2, 4. All right, so that's got 5 things in it, right? So what happens here is when you have to sort, right, we start out by splitting it in half, but what's going to happen is it's 5. You can't split 5 things in half. So we're just going to take, as close to half as you can, right? So we're going to take 3 and 2. And then when you split this up, same thing here. You're going to split the 3 in half. So you're going to get a 7 and a 3, and then a 5 just by itself. And then over here, you're going to get the 2 and the 4. Well, we're not done splitting in half because you got 7, and the 3. So what happens when you have like odd numbers is you end up like the 2 and the 4 are kind of at a higher level than the 7 and 3. So you have the 7 and 3, and then at this level, you've got these 2, this one, and this one. But there's nothing down here at the same level as the 7 and 3. But that doesn't actually matter in terms of forming the algorithm. You just kind of mirror this when you put it back together. So like the first thing you're going to do is you're going to put these together. So you're going to get a 3 and a 7, right? And you're back at this level now. Well, that's the same level as the 5. And it's the same level as the 2 and the 4. So you kind of just write them down there and merge those. So you get some weirdness at the beginning, but after that it works fine because like the 3, 7, and 5 can be merged into 3, 5, 7. The 2 and the 4 can be merged into 2, 4. And then these two get merged into 2, 3, 4, 5, 7. But I wrote it wrong. Like that. So again, you end up with kind of like nothing at this level. So you kind of only merge this bottom level first, and you kind of carry these down. So that's a little bit weird, but overall it's kind of the same here. And that's basically how MergeSort works. So what are the pieces to merge sort? Like, what do the algorithms really look like? So, um, like I said, there's basically two pieces: splitting the list in half and then merging it together. So, what you got is you got your algorithms are going to be uh, algorithm 9, which is merge sort, which looks like this. So procedure, merge sort, um, a list, and the list is A1, A2, dot, 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 AN, just like it was when we were sorting other lists. And here's how it goes. So it's going to say if n is greater than 1, right? So you only need to do anything if you only do something if you've got more than one element in your list, right? Because if you only got one element in your list, it's already sorted. So if n is greater than 1, you're going to have m is going to be the floor. I'm going to write the word floor, but they use the symbol in over 2. So what that's going to do is it's calculating basically where to split the, like where to cut this off, right? Like 7, 3, 5, 2, 4. Where's half? Uh, so, oh, actually, that's kind of interesting. I'm looking at the code. They're using floor here, which would mean that actually the first list is going to be the small list, right? Like I had 3 here and 2 here. It looks like their code would actually work the opposite way, like 7, 3, and then the 5 would be over here. It doesn't matter though, but it's only a difference between if you use floor and ceiling. Anyway, if n is greater than 1, then m for middle, is the floor of n over 2. And then what you're going to do is you're just going to have L1. That's your first list. So it's going to be A1, A2, up to the middle element. And then your second list is going to start at the next element, m plus 1, and then A, m plus 2, dot, dot, dot. And then, of course, you stop when you get to the end. So that splits your list. So now you've got your 2 lists, right? 2 lists. This is calculating the middle. And then we split it into 2 lists. So then what? Then all you're going to do is you're going to say, well, what we want to return is L. And L is going to be, you're going to have to merge, which we haven't seen the word merge before, but we're going to merge. And what we're going to merge is, well, we need to sort this first list, L1, and we need to sort L2. So what we're going to merge is, we're going to call merge sort on L1, and we're going to call merge sort on L2. And that's it. That's the entire thing. Now, they don't use, remember, they don't use end, but arrow end. Okay. And that is merge sort, because merge sort, which is what we actually wrote here, merge sort just splits it into 2 lists, right? It just splits L1 and L2, and then it calls itself, which is going to split L1 into 2. It's going to split L2 into 2. And then each of those is going to get split into 2. But once you're done splitting, you have to, right? Once it's all split at the middle point, you got to start putting them together. And so you need this other function called merge, and merge needs to know how to stick lists back together. So merge sort is the one that splits, merge puts them back together. So this does the splitting up lists, and then merge is going to put it back together, put lists together. Okay. All right, so let me just write down merge, and then we can, be done for today. Are you kidding me? I just want a box. Just give me a box. Come on, just draw a box. Just draw the box. What's in the box? Merge sorts in the box. Okay. Merge. All right. So how do we merge lists together? Well, algorithm 10. Merging lists. Okay. And I already talked about how to do it, right? Like if we have pre-sorted lists like this, like here's one, and I have another one, let's say like 5, 6, then the way you do it is you say you're just looking at the first two elements, 2 and 5, and then whatever one's the smallest you put in here, and then you cross it off. And now you look at the first two elements, the 5 and the 3, which is the smallest, 3, and cross it off. And now you compare the 5 to the 8, which is the smallest, 5, cross it off. Now you're comparing the 8 and the 6. What's the smallest? 6. Cross it off. And then now you just got 8. So you have that. All right. So that's how it works. And here's how it looks. So procedure. Merge. And what the input is L1 and L2. Sorted lists. So they have to be sorted before merge gets them. So sorted lists. All right. So the way you're going to do this is you're going to start out by making an empty list. All right. And then what you do is while both L1 and L2 are empty, sorry, non-empty. So while L1 and L2 are non-empty, what you're going to do is you're going to remove the smaller of the first elements of L1 and L2 and put it at the right end of L. All right. Now that's confusing, but it is what we actually just talked about here. So like, let me see if I can do this. Right? So the idea is you're literally just comparing these two, the 2 and the 5. Those are the first elements. Which one's the smaller? The 2. So you put the 2 into L, and then after you do it, it says remove. That's the cross out. So now that you've crossed it out, you're just going to keep doing that. So now you're comparing to the 5 to the 3, because the 3 is the new first element. And then you put it into L and you cross off the 3. And you're always putting it at the end of L, right? It always goes here at the end of L. And that's why they say the right end of L, right? The end of L, not the beginning of L. Okay, so you do that. Now, eventually what's going to happen is something like this, where one of your lists is empty. So you run this while loop until one of the lists is empty. When that happens, I guess still in the while loop, they say if this makes one of the lists empty, so if this makes L1 or L2 empty because you deleted the last element from the list, then what you're going to do is you're going to just, well, what would you do here, right? You just made this empty. So what you need to do is if you just make this empty, you need to come over here to the other list, and whatever's there, you just put on the end. So if this makes L1 or L2 empty, you just put the remaining elements from the other list on the end of L. All right. And then once you do that, you're done. So that ends the if statement, it ends the while loop, and then what you do is you return the L. Okay? And that algorithm in words was what we just did a few times here. Okay? And that's merge. Now, the problem with merge, you can probably tell, is that it's kind of tricky, right? It was a little bit tricky because they wrote it all in words and not something that looks like MATLAB. And that's why the code's going to be a little bit hard for you to write. And that's why I'm going to recommend that you come to office hours for help in order to get that done. I mean, we're going to go over it in lecture as well. But yeah, it's kind of hard to do that in MATLAB. So come to office hours for help. Okay, so it looks like we made it through this lecture. Finally, 2 in the morning. But there you go. I will talk to you guys next time. Yeah, see you then.